This is the digital image correlation portion of the final project for fracture mechanics. A brief overview of what we did in this project. We first apply a speckle pattern to the test specimen. We then use the test specimen to obtain a baseline error that meets our target. Our target is a class B1 extensometer, and this requires a max static strain error being less than 0.0001. After our static error looks good, we'll then apply displacement to the test specimen until total fracture. During this, we'll take pictures every 250 milliseconds. After this, we will post-process the pictures and get videos of first principle strain and normal strain. After this, we will draw conclusions on results and comment on the project overall. So here's our DIC experiment setup. This picture on the left was taken just before we ran the test. You can see the material test system. It's the two cells and then the basically everything else around the perimeter. We have our specimen loaded right here. And then our camera and tripod set up. This is our load chain. It's the two flanges coming from the top and bottom. And then all of this is flooded with blue light from our blue light lamp. And then on the right is just some specs about the camera that we used in case anyone wants to repeat this experiment. All right, so speckle pattern. We did a practice run prior to our day of testing. We wanted to make sure that we got a very good distribution of the black dots. This is very influential on the error that we get when we calibrate the software. So it took a while for us to get it down right, but after a lot of practice, Colin was able to get it down pretty good. Based on feedback from the students in the lab who had previously done DIC on different material or different objects, we kind of got this feedback from them. So up here we can see that they're very evenly distributed. However, they're very very scattered. You can see how light it looks. And then down here on the bottom, you can see still uniformly scattered but very dense. So we were aiming for this section here in the green box. This was our goal kind of density for our test specimen. Going to the actual test day now, we got the piece and spray painted it that day. It's very important that you don't let the spray paint dry overnight because then it becomes too brittle and it doesn't really stick to the test article as well as if it's still pliable. So here's kind of the matchup. So our goal is right here, and this is what the experiment camera sees with the blue light filter applied. You can see that it's pretty close to our goal. So we were pretty happy with the speckle pattern we got on test day. So here's the calibration process. So now that we have it loaded up into the machine, we don't apply any force or displacement to the specimen itself. We just let it sit there. And we take 20 calibration pictures. So in theory, this should all just be the same picture 20 times. However, due to noise and just the overall lab environment, any fluctuations that the camera will pick up, or any discrepancies it has with picking up certain dots, it ends up not being the same image. So after we have our 20 pictures, we then establish our area of interest. So this is this yellow grid that's applied. We exclude the notch here, so the software is only focusing on the parts of the specimen that are speckled. So step 3 in this is you have to give the software VIC2D a known dimension, and it's important that you can see this clearly in your image setup. So we decided to use this vertical distance here, and we measured this 3 different times and then averaged them. And you can see here our value was 38.66. I think after averaging, it ended up being about 38.67. But once that's in there, you can post-process all the photos now that the software knows the scale of the image that it's processing. And essentially it'll export a CSV of the error in each image from a reference image being the first image. And then you take the maximum of that, the absolute value, just make it positive. And our maximum error for this run was 9.19 e to the negative 5 millimeters per millimeter. And this fell within the class B1 range. So we hit our mark. We have a very good extensometer equivalent. So we're going to feel pretty confident in our analysis going forward. The experiment procedure, it's fairly simple. It's just pulling the test specimen apart at the two flanges at 10 millimeters per minute in the vertical direction until it completely fractures. Here is the video without any contours on it. So this is just going to be the images that we took. You can see here that displacement starts, and it's important to note if you pay attention to the angle between the specimen face here and the flange face right here, you'll see that grow as the displacement continues. And then on this left side here, you'll see a large amount of bending with a pivot point right around here. That indicates a lot of changing bending moments within the test article, but we'll talk about that later. It's just worth taking note of it now. So you can see here the crack starts to grow, and then it'll kind of stall out right here. And when you see the large amount of bending here, this will actually snap in a different direction, and then it snaps apart. We'll dive into that a little bit more later. But again, just with my mouse out of the way, there's the same video again. Fairly constant rate for the first crack propagation, pretty smooth, and then it gets kind of messy towards the end. Messy and quick. Moving on, here is the video of the first principal strain. This is the same video, just with the contour plot mapped over it. So that one runs a bit quicker, so we will play it again. You can see the strain right ahead of the crack tip propagation grows really quickly, which you'd expect to see as the material where the crack is propagating through is expanding really quick until it can't hold it anymore and it cracks. So these red areas are where we hit our peak. It's important to note that our boundaries over here are fixed. So this is fixed at 0.338, which is where it hits its max right when it pivots to the other direction. And then negative 0.004 was just hard coded in as our low point. It was really difficult to get good videos of these. We'll talk about it more later, but a lot of tweaking had to be done. Had to be done to the parameters and tolerances for the post processing. Here is the video of the normal strain. Maybe. Once again, same exact video, just with the contour put over it for the normal strain. That runs pretty quick, so we'll play it again. You can see very similar behavior than when compared to the principal strain. Here, the max that we're given is 0.324. That's once again seen when it changes direction at this peak here. And then the hard-coded minimum for this is 0.016. See on here, it's kind of acting weird. Okay, moving on. Here's some pictures of the specimen after failure. So here we see very sharp, almost 90-degree changes in the crack path. You can see a very slight one down here, and then the initial large one here. This here on the right side is going to be the bottom piece, but looked at from kind of a obscure angle. You can see the spray painted face here, so we're looking at the back. But again, it's just another visual of this kind of stepped fracture that we see. Just some basic observations from the video and the pictures that we collected. After applied stress exceeds yield strength, the material near the crack tip underwent viscoplastic deformation, and the crack started to propagate. Throughout crack growth, the specimen experiences increasing bending moments. Just going back to the original video that we saw, you could see the angles changing between the flange face and the specimen face, and then that whole left side again bending, almost in a V, sideways V, I guess. At the start, crack growth occurred at about 45 degrees from the horizontal crack tip. This indicates that there's a weaker interface on the 3D printed part. This basically aligns with the layer orientation. So this was, you can tell the way that this was 3D printed because starting out, the crack grows right up one of the layer's orientations. But then you see, once you hit that peak, it changes 90 degrees, and that's basically the initial mode 1 fracture switching and mixing with mode 2 because of how much the piece deforms. So it snaps to that other layer orientation and then travels some more. And let's actually go back. So it snaps to the other layer orientation here, and then snaps back to the original one, and then snaps back again to the other. So again, that's kind of that stepped fracture pattern that we're seeing. And then here is just the max normal strain and principal strain. They're very close to each other. And this indicates that the principal strain is closely aligned with the y direction of the specimen. It's important to note that these values might be slightly exaggerated. You see the same trend in both strain contours. However, if you look right when we get up to that peak, you can see that it's the red zone here is still picking up strain. It doesn't realize that there's a crack there. It thinks that this dot that used to be right next to this dot is just strained that much. Doesn't realize that it is separated. So these strain values that we're getting here for our max might be exaggerated by these. However, this is still where the max strain happens. It just might be a little bit lower than what we're given as output. It's just important to note that. Just some notes about post-processing. Like I said earlier, some tweaks were definitely needed to get clean videos of strain. Prior to the tweaks, we actually were picking up the entire crack all the way down to the start of it. So we were getting some pretty crazy values. But thankfully, Artur got us in a pretty good spot with our videos. Just one example is we increased our subset size to 19 to get stress concentrations to fall on the crack tip. A lot of other changes were made in confidence intervals and tolerances, but we're pretty happy with how the videos turned out. I already kind of mentioned this, values may be exaggerated. And then just touching again on the bending, you'd expect to see some strain in the bent area. So like if you look at that left side, let me go back up. So when this starts to bend, you would expect to see some strain here. And some of the reasons we think we don't see it is either one, this hard-coded lower bound, this strain being negative might be just not, it might be above this threshold, so it just doesn't show up any differently. Another reason is that the strain values could be showing up on the backside of the specimen out of view of the camera. Um, this would imply some mode 3 um, fracture or mode 3 stress. Um, it's just something to note. We're not too entirely sure. Those are our two best guesses as to why we aren't seeing the strain there. And then suggested future DIC work. If you do happen to know the Young's modulus and the Poisson ratio at the time of the post-processing, then you can obtain your stress fields. We didn't know that at the time of our post-processing, so we had to just leave it at strain. But I mean, you'd see the same trends as we did in our videos here. Yes, that is it for DIC, digital image correlation. Looks like we're moving on to failure analysis. All right, thank you.